All right, we're going to be taking another step towards understanding why the energy levels in electrons are the way they are. So let me share the tablet here. So the learning objectives for this segment are going to be, when they come up, there we go. Using the de Broglie equation to describe the wave nature of matter now instead of light, and use the Heisenberg uncertainty principle to describe uncertainty in atomic particles. So the question is, how do electrons and atoms behave? Niels Bohr proposed in 1914, as we mentioned, a model of the hydrogen atom as a nucleus with an electron circling around it. And only specific orbits with specific energies are allowable. When the electron falls from a higher energy outer orbit into a lower energy inner orbit, it emits electromagnetic energy, and the frequency of that energy coming off corresponds to the difference between the two orbits. And the exact same when it absorbs energy. If it absorbs energy of the right frequency, then it can jump from a lower orbit to a higher orbit. Now, this doesn't make sense compared when you consider classical things like a satellite orbiting the Earth. So the satellite orbiting the Earth can take any level that it wants to. Additionally, we know that the electron is negatively charged and the nucleus is positively charged. So they attract each other. It shouldn't orbit at all. It shouldn't get stuck. It should just crash into the nucleus, releasing a whole lot of energy. So something else is going on here. Matter doesn't behave classically. It behaves in a different way. So yeah, this is just review of the numerical results that we got that the atoms, the emission spectra or the absorption spectra of atoms corresponded to these very distinct mathematical relationships, had these clear mathematical relationships that looked awfully suspicious. So the Rydberg formula is just for H, but the concept applies to all atoms and molecules. They're discrete orbits the electrons can go in. Okay, so if an electron doesn't behave like a normal satellite going around, what could be the possible reasons? So Louis de Broglie in 1924 suggested that if a light can behave in some respects like matter, then perhaps matter can behave in some respects like light. In other words, perhaps matter is wave-like as well as particle-like. So what is the wavelength of a particle like an electron? Before we handle that pressing question, we're going to handle one more pressing question, which is the pronunciation of de Broglie. It's not de Broglie, it's de Broglie. It's a French word. He's a French aristocrat who started dabbling in science. Turned out he was pretty good with it, pretty good at it. So de Broglie, he proposed that matter can have wave-like properties. How do we figure out what the, can we come up with a formula that would describe the wavelength of an electron? So you can show that the momentum of light is proportional to the energy, and so we have the momentum of light being E divided by the speed of light. The Planck-Einstein equation, which we saw before, is that each light particle, each photon has energy equal to Planck's constant times its frequency, and we have the wave relationship. The frequency is equal to the speed of light divided by the wavelength. So you can rearrange all of those and solve to get that the wavelength should be equal to well, the wave for the light, the wavelength is equal to Planck's constant divided by the momentum. Well, if that's the case, what if we say that that holds for matter particles as well? That the wavelength is the Planck constant divided by the momentum, which for a massive particle is just the mass times the velocity. That's the definition of momentum. So we'll assume it and see where that gets us. So this is the de Broglie hypothesis. The wavelength is equal to Planck's constant divided by the classical momentum. And ended up winning a Nobel Prize 5 years later because people found that matter did indeed sometimes behave like particles. Matter did behave like waves. Again, de Broglie. Okay, so what was actually done is to use this double slit experiment, but with electrons. So as, for classical particles, that if you have some slit, you shine a particle beam on it. We have particles accelerated, so they're going straight out. You would get, with a double slit, you get two bright spots, and those are the places where the two smaller beams of particles that go through the slot end up. But when a beam of electrons goes through two closely spaced slits, if you're careful about the setup and you put the slits very close to each other, then what you can actually get is an interference pattern, just like you see with waves. And the spacing between those will depend on the energy, will depend on the momentum of the electrons that are going in. So this experimental verification showed that yes, indeed, sometimes matter could behave like waves, and it behaved according to the de Broglie hypothesis for what that wavelength would be. Now, there is a quantum mechanical thing here that holds for both photons and electrons. If you keep track of which of the double slits each individual electron or photon goes through, you don't get an interference pattern. You just get two bright spots. And that's a really complicated measurement issue in quantum mechanics that we won't go into. And we don't need to here because you never actually localize electrons